everyone, I'm Navya Paramesha. Welcome to today's video on binary tree searching, essential for learning data structure and computer science. So in this session, we'll explore binary tree search and types of tree searching. This presentation will provide a comprehensive overview of BFS, that is breadth first search, and DFS, depth first search algorithms, exploring their definitions, characteristics and practical applications in various fields. So what is binary tree? A binary tree is a hierarchical data structure in which each node has at most two children, commonly referred to as left children and left child and right child. It it's called a tree because of branch-like structure, and binary because each node can have up to two connections downward. What is tree searching? A tree is a hierarchical data structure made up of nodes. The topmost node is called the root, and every node can have child nodes. So searching a tree means visiting the nodes in a specific order to either find a specific value, explore the entire structure, perform an operation on each node like printing, summing, or modifying data. Structure of binary tree. Each node in a binary tree contains a data, the actual value, may be a number or a character, left child, a reference to the another node or null, right child, a reference to the other node. In the sense, A is the root node and B is the left child and C is the right child. A is the root top node, B, C are children of A and D, E are children of B. F is a child of C, so D, E, F are the leaf nodes since it does not have children. So key terminologies in binary trees. Root. The topmost node of the tree is known as root. Leaf. A node with no children are known as leaf. Edge. The connection between parent and children nodes are known as edge. So depth. The number of edges from the root to a given node is referred to as depth. Height. The number of edges on the longest path from a node down to a leaf. Subtree. A tree formed by any node and its descendants. And sibling. Nodes that share the same parent are known as sibling. Parent or child. Basic hierarchy. On one node is above another in a connected path. Operations on binary trees. Insertion. Insertion refers to adding a node at the appropriate position. Deletion. Removing a node while maintaining tree structure. Traversal. Visiting nodes in certain order. DFS or BFS. Search. Finding if a value exists. So breadth first search. Breadth first search is an algorithm for traversing or searching tree or graph data structure. It starts at the root node and explores all of the neighbor nodes at the present depth prior to moving on to nodes at the next depth level. This method guarantees the shortest path in unweighted graphs. Implementation of BFS. BFS explores horizontally, it visits all nodes at one depth before moving to the next. A queue maintains the order. Nodes are processed in a first in first out manner. So BFS reliably finds the shortest path in unweighted graph. This is a key advantage. Assume we want to traverse a tree using BFS. The first step is to add node A to the queue and mark it as visited. So then we dequeue node A from the front of the queue and visits its children, which are B and C. We add nodes B and C to the back of the queue as they are next level of the nodes to be visited. So next we dequeue node B from the front of the queue and visit its neighbors, which are nodes D and E. We add nodes D and E to the back of the queue as they are next level of the nodes to be visited. We then dequeue node C from the front of the queue and visit its neighbors, that also known as children, which are nodes F and G. So we add nodes F and G to the back of the queue as they are the next level of the nodes to be visited. We continue dequeuing nodes and visiting their neighbors until the queue is empty. The final order of the visited nodes using BFS is A, B, C, D, E, F and G. Application of BFS. BFS is widely used in various applications such as finding the shortest path in unweighted graphs, network broadcasting, and in algorithms for game AI, where it examines all possible moves at each level. BFS is also employed in social networking applications to find all connections or friends of friends and in web crawling algorithms to index pages. Depth first search. Depth first search or DFS is an algorithm for traversing or searching tree or graph data structure. It starts at the root node and explores as far as possible along each branch before backtracking. So DFS can be implemented using either a recursion or an explicit stack. Implementation of DFS. So DFS explores as deeply as possible along each branch before backtracking. It fully explores on path. DFS typically uses a stack. This can be explicit or implicit through recursion. DFS has in-order, pre-order, and post-order traversal, each having unique applications. So let's see how the depth first search algorithm works with an example. We use an undirected graph with the 5 vertices. So this is an example for undirected graph with 5 vertices: 0, 1, 2, 3 and 4. So we have block visited and stack block. So we start from vertex 0. The DFS algorithm starts by putting it in the visited list and putting all its adjacent vertices in the stack. So 0 is put in the visited list and the rest of them are put in the stack block. Next, we visit the element at the top of the stack, that is 1, and go to the adjacent nodes. Since 0 is already being visited, we visit 2 instead. So since 0 is already being visited, we'll take the 2 into the project. And vertex 2 has an unvisited adjacent vertex in 4. So we add that to the top of the stack and visit it. Then we proceed further by visiting element 3. After we visit the last element 3, it doesn't have any unvisited adjacent nodes, so we have completed the depth first search traversal of the graph. So application of DFS. DFS is utilized in various applications such as topological sorting, solving puzzles with a single solution like mazes or Sudoku, and in pathfinding algorithm. It is also used in AI for searching through complex decisions trees and in backtracking algorithms where all possible solutions are explored. Characteristics of BFS and DFS. Uses. DFS uses the stack, whereas BFS uses the queue. And in DFS, lower and narrow trees, and BFS can be high in wide trees. And the shortest path cannot be guaranteed in DFS traversal, whereas the main virtue of BFS is to find the shortest path. And DFS is faster in deep but sparse trees, but BFS is faster in for shallow trees. And in implementation, DFS is easier with recursion, whereas breadth first search or else BFS is not in that way. Real-time scenarios are finding shortest path, like in maze, BFS are used, and solving puzzles with one solution like Sudoku, DFS are used in that, and finding connectivity like friends, DFS are used, and checking bipartite property in graphs, BFS is used, and game tree exploration like chess, DFS is used in that. In conclusion, breadth first search (BFS) and depth first search (DFS) are two essential algorithms used to traverse or search through trees and graphs, each with its own strategy and advantages. BFS explores a structure level by level, starting from the root and visiting all neighbor nodes before moving deeper. This makes it particularly effective for finding the shortest path in unweighted graphs or when solving problems that require layer-wise processing, such as social networks or routing system. On the other hand, DFS dives deep into each path before backtracking, making it ideal for problems involving complete exploration like maze solving, puzzle generation, or checking for cycles. While BFS relies relies on a queue and tends to use more memory when dealing with wide trees. DFS uses a stack or recursion and can be more memory efficient in narrow or deep structure. Both algorithms are fundamental to computer science and are widely used in various domains. Understanding how they work and when to apply them is crucial for solving real-time computational problem efficiently. So that brings us to the end of our overview on binary trees. We have covered the concept, structure and practical applications, and I hope this session has made binary trees much clearer for you. Thank you.